You clear your browser cookies, activate a VPN, and open an incognito window. You believe you have severed the link between your physical identity and your digital footprint. But mathematically, you have merely closed your eyes. In the vast architecture of data, your absence of standard identifiers creates a highly specific negative space. You are no longer a name, but you have become a digital ghost, a precise, high-dimensional vector that points exactly to you. To understand how easily this ghost is materialized, consider the 2006 Netflix prize. Netflix released a dataset of 100 million movie ratings. They stripped away all names, usernames, and obvious identifiers, leaving only user IDs, movie titles, ratings, and dates. It was considered perfectly anonymous. However, researchers Arvind Narayanan and Vitaly Shmatikov realized that human behavior is inherently unique. By cross-referencing this anonymous data with public reviews on the Internet Movie Database, they completely de-anonymized the dataset. This wasn't a failure of redaction, it was a fundamental misunderstanding of geometry. Today, we will deconstruct the exact mathematical pathways through which your identity leaks, explore the terrifying curse of dimensionality, and build from scratch the rigorous geometric defenses required to protect human privacy in the algorithmic age. The illusion of data anonymization was first shattered in 1997. The Massachusetts Group Insurance Commission released anonymized data showing the medical diagnoses and prescriptions of state employees. They removed names, addresses, and social security numbers. William Weld, the governor at the time, assured the public that patient privacy was mathematically secure. Enter Latanya Sweeney, a computer science graduate student at MIT, who suspected the state's definition of anonymity was profoundly flawed. Sweeney purchased the public voter registration rolls for the city of Cambridge for $20. The medical dataset contained 3 seemingly harmless attributes: ZIP code, birth date, and gender. The voter rolls contained these exact same 3 attributes, but crucially, they also included names and addresses. Sweeney simply performed a set intersection. She filtered the voter rolls for the governor's ZIP code, his exact date of birth, and his gender. The result? Only 6 people in Cambridge shared the governor's birth date. Only 3 of them were men. And only 1 lived in the governor's specific ZIP code. Sweeney had successfully extracted the governor's private medical records. She later proved mathematically that 87% of the population in the United States can be uniquely identified using only these 3 pieces of information. Privacy is not about hiding your name, it is about hiding your coordinates. To understand why 3 attributes are so devastating, we must translate identity into geometry. Imagine a one-dimensional line representing age. You are just a point on this line, sharing your coordinate with millions of others. Now, add a second dimension, income. You are now a point on a 2-dimensional plane. Add a third dimension, your ZIP code. You are now a point floating in a 3-dimensional space. With each new attribute, the space expands. But modern databases do not stop at 3 dimensions. Your smartphone tracks your location every minute, your browser logs every click, your smartwatch records your heart rate. Every distinct piece of data is a new orthogonal axis. You are no longer a point in a 3-dimensional room, you are a vector in a space of thousands, or even millions, of dimensions. And in high-dimensional space, the laws of geometry begin to warp. This brings us to a terrifying mathematical phenomenon known as the curse of dimensionality. Let us look at the volume of an n-dimensional sphere, or n-ball. The formula for the volume is pi to the power of n over 2, divided by the gamma function of n over 2 plus 1, all multiplied by the radius to the power of n. Notice the gamma function in the denominator. As the number of dimensions, n, increases, the gamma function grows factorially. Because factorial growth vastly outpaces the exponential growth in the numerator, a bizarre thing happens. As you add more dimensions, the volume of a unit sphere eventually shrinks and approaches absolute zero. What does this mean for your data? It means that in high-dimensional space, the center of the space is entirely empty. All the volume, and therefore all the data points, are pushed to the extreme outer shell of the space. This geometric hollowing out creates extreme sparsity. In a space of 1,000 dimensions, the distance between any two random points becomes almost identical, and incredibly vast. You are mathematically isolated. There is no one near you. Because you are so far away from everyone else, any attacker only needs to know a tiny fraction of your coordinates to pinpoint you entirely. Your digital ghost is utterly alone. To combat this isolation, cryptographers initially proposed a concept called K-Anonymity. The rule is simple: a dataset provides K-Anonymity if the information for any given person cannot be distinguished from at least K-1 other individuals in the dataset. If K equals 5, your exact combination of attributes must be shared by at least 4 other people. If you are unique, the database administrator suppresses or generalizes your data. But remember the curse of dimensionality. Generalizing data works in 3 dimensions, but in 1,000 dimensions, making you identical to 4 other people requires erasing almost all of your useful data. If you blur a high-dimensional vector enough to hide it, you destroy the utility of the dataset entirely. K-anonymity is geometrically incompatible with the modern reality of big data. The situation grew darker in 2003, with the publication of a landmark paper by Irit Dinur and Kabi Nissim. They proved a devastating fundamental limit of information theory. They asked a simple question: what if we don't release the database at all? What if we only allow researchers to ask statistical questions, like, what is the average age, or, how many people have this disease? Surely, aggregate statistics are safe. Dinur and Nissim proved mathematically that if you answer enough aggregate queries with high accuracy, an attacker can reconstruct the entire underlying database. It is a system of linear equations. Every query provides a new equation. Once the attacker asks enough questions, they have enough equations to solve for every single unknown variable, meaning every individual's private data. The vault is shattered not by a drill, but by algebra. Privacy was mathematically broken. The scientific community needed a paradigm shift. In 2006, Cynthia Dwork, Frank McSherry, Kabi Nissim, and Adam Smith introduced the ultimate geometric defense: differential privacy. Differential privacy is not a software tool or an algorithm, it is a rigorous mathematical definition of what privacy actually means. Here is the defining inequality. The probability of an algorithm outputting a specific result, S, on a database, D, must be less than or equal to e to the power of epsilon, multiplied by the probability of outputting that exact same result on database, D'. Database D' is identical to D, except for the addition or removal of one single person. Let's break down this profound equation. What this equation guarantees is plausible deniability. It means that whether your specific data is in the database, or completely removed from it, the output of the algorithm remains virtually indistinguishable. An attacker looking at the final result cannot mathematically determine if you participated in the dataset. Your presence or absence has been structurally decoupled from the output. The variable epsilon is the privacy budget. It controls the maximum allowed distance between the two probabilities. If epsilon is 0, e to the power of 0 is 1. The probabilities must be identical, meaning absolute privacy, but zero utility because the algorithm can learn nothing. As epsilon grows, the privacy guarantee weakens, but the utility of the data increases. It is a precise dial tuning the geometry of the data. But how do we achieve this inequality in practice? The most common method is the Laplace mechanism. To prevent the Dinur and Nissim reconstruction attack, we cannot give exact answers to aggregate queries. We must inject carefully calibrated mathematical noise. The Laplace distribution is a symmetric probability distribution with a sharp peak at 0, and exponential tails. If a researcher asks, how many people have a specific medical condition, and the true answer is 42, the algorithm samples a random number from the Laplace distribution. It might add -2.3, outputting 39.7. The next time, it might add 1.5. The true answer is obscured by a fog of probability. The width of this fog is strictly determined by our privacy budget, epsilon. Geometrically, differential privacy transforms your precise point in high-dimensional space into a fuzzy, overlapping probability cloud. Because the noise is calibrated to the maximum impact any single person can have on the query, the probability cloud of a database containing you overlaps almost entirely with the probability cloud of a database without you. The attacker is left grasping at vapor. Differential privacy also possesses a profound property, the composition theorem. It states that if you run multiple differentially private algorithms, the total privacy loss is simply the sum of their individual epsilons. This allows mathematicians to rigorously track exactly how much privacy is leaking over time. Once the total epsilon budget is exhausted, the database must be locked down. No more questions can be asked. There are two boundaries to this defense. In central differential privacy, you must trust the database curator, like Apple or Google, to hold your raw data and add the noise themselves. But in local differential privacy, the noise is added directly on your device before the data ever leaves your phone. You flip a mathematical coin. If it's heads, you send your true data. If it's tails, you send a random lie. The server only sees the noisy aggregate. But what if we want to compute exact functions without adding noise, while still maintaining absolute privacy? This requires a topological transformation known as homomorphic encryption. It allows a server to perform mathematical operations directly on encrypted ciphertexts. You encrypt your data, send it to the cloud performs the machine learning matrix multiplications on the encrypted gibberish and sends you back an encrypted result. Alternatively, we can invert the flow of data entirely using federated learning. Instead of sending your high-dimensional vector to the central algorithm is sent to your device. The neural network trains locally on your raw data. Then, only the mathematical gradients, the tiny adjustments to the network's weights, are encrypted and sent back to the server. Your digital ghost never leaves the physical boundary of your hardware. We are faced with an eternal, inescapable trade-off curve. On the x-axis, privacy. On the y-axis, utility. We need vast amounts of medical data to cure cancer, and massive behavioral datasets to train artificial intelligence. But without mathematical guarantees like differential privacy, achieving that utility requires sacrificing the individual. We become nothing more than exposed coordinates in a machine's latent space. The most chilling aspect of the digital ghost is its immortality. In physics, entropy only increases. In information theory, once a high-dimensional vector is leaked, the entropy cannot be reversed. You cannot unpublish data. You cannot change your date of birth or your genetic sequence. If your precise coordinates are exposed today, they remain exposed for the rest of your life. Trusting corporate promises is a structural vulnerability. True privacy can only be guaranteed by the cold, unforgiving laws of mathematics. We must demand systems built on cryptographic proofs, not privacy policies. I am Lemma, and if you want to continue exploring the hardcore mathematical architecture of our reality, subscribe to the channel. Hit the like button to signal the algorithm, and share this video to help others understand the geometry of their own digital ghosts. Until next time.